Welcome to a series of lectures called Glass, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair of Glass and Glass Ceramic. This video series is intended to give background information on selected aspects of glass science and to reinforce the content of the lectures. The videos are not based on the structure and thematic sequence of the lectures, however. In this video, we will have a closer look at Tammann curves and at the glass forming tendency. Let's first consider a melt that is cooled down. So at the point of the crystallization temperature, the crystallization starts and we have two phases, a liquid phase and a solid phase in an equilibrium. So we have the existence of these two phases and the temperature of the system stays constant until the complete melt is crystallized. Then we achieve a polycrystal that cools down according to its thermal properties. Now, if we look at the sequence of crystallization more closely, we see that a certain undercooling is needed for the formation of nuclei that initiate the crystallization. So, in general, a melt is undercooled until a certain point where nucleation starts. On these nuclei, the crystals grow, the crystallization enthalpy is released, and the temperature of the system increases again exactly to the level of the melting temperature, and then the aforementioned two phases coexist and the melt crystallizes. So the undercooling is a very important point and is essentially needed for initiating the crystallization. If we undercool the melt further below the point where the nucleation can start, we achieve the state of a metastable equilibrium, which we know from glass transformation. And if the undercooling is continued further, we come to the point of the glass transition. And after the glass transition at lower temperatures, the liquid is no longer in a thermodynamic equilibrium and we receive the respective glass. Now, as mentioned, each crystallization needs a nucleation, and the nucleation needs to take place before the crystal can grow. Both processes, the nucleation and the crystal growth, follow a certain thermodynamic and kinetic boundary. If we plot the rate of the nucleation or the rate of the crystallization or the crystal growth in a diagram where we have here the decreasing temperature, first, at the liquidus temperature, the crystals could grow, but there is no nuclei available, so the crystal growth does not start. Then, at a certain point, the nucleation starts, and when the nucleation has started, crystals can grow. However, if the curves overlap, like shown in this picture here, there's only this small window between the maximum nucleation temperature and the minimum crystallization temperature at which crystallization can occur, because only in this temperature range, nuclei and crystals are generated in parallel. If we are in this temperature range here, the crystals could grow, but there are no nuclei available. If we are in the temperature range here, nucleation is taking place, nuclei are available, but the crystal growth cannot take place anymore. Now, to achieve a crystal growth, the undercooling is mandatory. This area here, as mentioned before, is the area where both processes overlap and both nucleation and crystallization can take place. However, this area is not so much desired because it is a time-dependent process, and the first nuclei that have grown already provided the basis for them crystal growth, but in parallel even more nuclei grow, meaning we get a quite heterogeneous structure. already grown crystals grow further, new formed crystals start growing, and the structure is usually not what is desired. If the two curves of crystal growth and nucleation do not overlap, when cooling down below the liquidus temperature, there is no chance that nucleation and crystal growth take place in parallel. The curves are fully separated, and either crystal growth is available, but no nuclei are formed, or nuclei would be available, but no crystal growth can take place. This type of behavior between the two curves is most favorable for glass forming, because no crystallization can take place when the melt is cooled. And these two curves, plotted in this way, resemble what we call the Tammann curves. So, in summary, one can say for a good glass forming ability, the distance between the crystallization temperature minimum and the nucleation temperature maximum should be as large as possible. Let's get back to the overlapping curves. In this diagram, different areas of the Tammann curves can be identified. There is the area between the liquidus temperature and the maximum nucleation temperature. In this temperature range, only crystal growth takes place. This is called the Ostwald-Miers area, meaning if nuclei have been formed at a defined state at lower temperature and the glass is heated to this temperature range here, the crystal can grow without any further nucleation, and by this a quite homogeneous structure is generated. Also in this area, theoretically, if one would implement seed crystals to this melt, or seed nuclei, the melt would readily crystallize. Let's have a look at the driving forces for the crystallization or the crystal growth and the nucleation. Each curve has an incline with decreasing temperature. This is the so-called thermodynamic driving force, and it is mainly depending on the increased undercooling, as we can see here. On the other hand, both curves also have a decline here, and this decline basically depends on the increasing viscosity, which limits the movements of the atoms or the molecules which are needed to form the crystals or the respective nuclei. And the temperature for the nuclei is less viscosity dependent because the nuclei are smaller and can grow even at lower temperatures. But for the crystal growth, the temperature is larger because for crystal growth, larger diffusion and atomic movements are necessary. And this dependence here is resembled by the diffusion coefficient, which also is depending on the viscosity in this kinetic barrier equation. Real-life Tammann curves can look like these two examples here. On the left side, we have an example of a good glass-forming melt because the crystallization rate and nucleation rate are completely separated from each other. So there is no chance that crystallization and nucleation can take place parallel. On the other hand, on the right diagram, the nucleation curve and the crystallization curve overlap. These are melts with a poor glass forming ability, for instance, metal melts, because it doesn't matter in which temperature range the melt is, nucleation and crystallization can take place in parallel. And this is also the explanation why metal melts crystallize so easily and why it is so difficult to make metallic glasses. This situation can only be overcome with very high cooling rates to avoid any crystallization. With this, we are at the end of this video, and I trust it was helpful for your further understanding of glass science.